Et on va poursuivre donc dans la prise en compte, effectivement, la façon de prendre en compte effectivement les comportements dans l'éco-conception, dans la conception effectivement de l'urbanisme, de la ville de demain, des bâtiments, des modalités de transport et autres. Donc, comme je vous disais, il y avait 2 interventions qui vont se dérouler en anglais, pardon, excusez-moi. Et donc, je vais commencer par appeler Darren Robinson, s'il vous plaît, qui est professeur donc à l'Université de Nottingham au Royaume-Uni et spécialisé en énergie et développement durable. Je vais poser ma question en français, puis je vais la poser également en anglais. Quelle est la part, je voulais vous interpeller sur la part quelle est la part finalement du déterminisme et celle de l'aléatoire dans le comportement des occupants d'un logement. So, you are a professor in Nottingham University, specialized in energy and sustainability. And I'd like to ask you, what is the part of the determinism and of the unpredictable in the flat occupants behavior, please?
Ok. Tout d'abord, je vous offre mes excuses parce que même si je comprends quelques notions de base en français, je vais quand même vous parler en anglais. So, here we go. So all behaviours are, in a way, some kind of combination of, let's say, deterministic relationships superimposed onto which there is randomness. So our behaviours are stochastic in nature. There isn't any kind of human behaviour that I'm aware of which is purely deterministic. There is always randomness associated with what we cannot know or what we do not know. And well, so what I'm going to be presenting about is a reflection of that.
I want to just if you can respect 20 minutes, because we want to have a discussion with all the people at 4. So we have 4 interventions before. So please.
Okay. So normally when I talk and I present stuff that I'm excited about, I talk quickly. So I'm going to talk even quicker. So good luck. Okay, so based on what we were just talking about, then people's decisions depend on both deterministic and random responses to stimuli. They are stochastic. The same person may respond differently on different days, even when the underlying stimuli are the same. We might have a different mood, we might have different concentration levels depending upon what the task is that we're conducting at the time, which means that the response of our response to these underlying stimuli is going to vary from one occasion to another. Our responses also vary between individuals, and I'll show you some results a little bit later which exemplifies that, but I think Eric, in his excellent presentation earlier, gave some examples of different activities amongst different demographic groups in the population of France. And these behaviours have significant implications not only for energy, but also for comfort and overall well-being amongst the occupants of homes and workplaces. So we want stochastic models. We want models that embrace this randomness in a way which enables us to make meaningful predictions, that account for the range of types of behaviours. So I'm interested in predicting the probability with which firms and individuals are going to invest in measures to improve the performance of their homes and workplaces. But I'm also interested in predicting when people are likely to be present, the activities that they're likely to be performing whilst they're present, and the kinds of behaviours they'll conduct depending upon those types of activities. And those behaviours might involve interactions with the envelope of buildings, might involve interactions with their own personal characteristics, their clothing level, their activity level, their posture. and these have implications for their satisfaction. We want to account for variations over time and, of course, between individuals. And we want to do this to provide better inputs to our simulations so that we're able to make more robust renovation and design decisions. So we've got better load profiles for the sizing and control of energy systems, whether they be building embedded or district-wide, so that we're able to ultimately also predict with greater certainty energy use in buildings. So I'm not going to bore you with the mathematics, but I'll maybe describe just some in words the underlying issues. So we use broadly speaking, three modeling tools in my group to predict these stochastic processes. So one is a really simple family of model or type of model, which we express as a Bernoulli process. So that's simply predicting the probability with which a particular state is likely to be observed. So that could be a model that predicts the probability that a window is found to be in the state open, that a light is found to be in the state on, that a computer is found to be in the state on, that we are observed to be undertaking the activity sleeping, etc. And we normally begin, okay, so I should maybe just explain one thing. So it's quite difficult to... Okay, so in this type of model, it's called a generalized linear model, where we have a logic link function. So we've got an intercept over there, and we have a slope associated with each of our set of k predictors. We normally start with a model with just a single predictor, and then we keep adding other predictors, but only whilst they they increase our predictive power, only whilst they are useful. Okay, so basically the reason there's this crazy-looking monk is to illustrate the point that we try to apply the principle of Occam's razor. We're trying to shave away any unnecessary detail from our models. We want our models to be parsimonious. We want them to be as complex, well, as simple as possible, but no simpler. Okay, we don't want them being overly complicated. If I go back to this graph, then on the x-axis, you'll see an explanatory variable, so it's just indoor temperature, and on the y is the percentage or probability with which we observe a window to be in its open state. Okay, so we can, if the indoor temperature happens to be, let's say, 25 degrees, we can determine the probability with which we observe the window to be in its state open. Then we draw a random number. If the random number is less than that probability, then we predict within our simulation program that the window is going to be open. Yeah? So, as indicated here at the bottom, then the disadvantage of this is that we're not properly resolving for dynamics of interactions. So we're not properly resolving for the transition events. So when a window transits from being closed to being open or open to being closed. So to handle that, forget the maths, to handle that we can model the process that we're interested in as a Markov process, which enables us to explicitly resolve these or predict these transitions in state. Okay? So I'll just skip all that. So here we've got, well, most of it anyway. So here we've got a 2x2 state transition probability matrix, where in rows we've got the present state, and in columns we've got the future states. So upper left, we've got the probability with which a window was closed and it stays closed, for example. And on the right, we've got the probability with which a window was closed and it transits to being open. Okay? And here we've got a cumulative distribution function that represents the sum of those, well, those two probabilities. And in the uppercase, it's the sum of the two, right? So now we can draw a random number. And if we're interested in the probability with which the window stays closed, and we draw a random number and that's less than that probability, then it does stay closed. If it's greater, then it transits to being open. Okay? So we're properly modeling the transitions in status. The problem with these discrete time Markov processes is that a lot of the time transitions don't take place. That means that we're doing redundant calculations. So we're undertaking computational effort for no outcome, and that's a bit pointless. So what we can do to get around that, I'll skip the maths again, is to resolve the process as a continuous time random process. So that means that we're explicitly predicting the duration for which a particular state will survive, okay? So here, these curves are all parametric curves which express the probability with which a window is likely to survive in its open state, given the indoor temperature that occurred at the time, okay? So now we can choose the right curve that corresponds to our indoor temperature. We can draw a random number. Where the random number intersects that curve, we can read down and predict the duration for which the window is going to survive in its open state, okay? So we've got now one computation which has avoided perhaps 10 or 20 computations had we used the discrete time Markov process approach. So in our work, we often use either pure versions of these three processes or hybrids of them. And it tends to be that hybrids are the most effective. So here's an example where we've just used an inhomogeneous Markov chain, that's that Markov process, to model the probability with which we observe people to be present, or rather, the probability that people are present, accounting for the transitions. So on X, on X, we've got time, and on Y, we've got the probability that a person is present. In blue, it's what we observe, and in red, it's what we predicted using our model. Okay, so you can see that there's pretty good correspondence. I should say that these are in units of 15 minutes of time, so 96 corresponds to 24 hours for the first day. So we've got Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Eric mentioned earlier that a very powerful source of data describing activities is time use surveys. So in the UK and many other countries, sociologists, or social scientists, I should say, conduct surveys of the use of time, where for 10-minute time slots, people complete a diary entry that describes what activity they were performing. So here's an example of where we first plot what people are doing. We've identified 10 aggregates of activity that we're interested in with respect to the prediction of energy use in buildings. So we've got sleep, we've got passive, that means that we're awake, but we're not really doing anything. Audio visual, we're using IT equipment, we're cooking, etc., etc. And below, so here are the results of a simulation where we've predicted transitions from one activity to another and then predicted the duration for which that activity survives before we transition to the next. And you can see that there's pretty good correspondence. I think Eric was really making the point earlier as well that we need to take into consideration that there are cultural differences, that behaviors may differ from one country to another. I think this is hilarious. So on the top left, we've got the probability with which the activity food and drink preparation takes place in the US, okay? And bear in mind that the probability that a cooker is going to be switched on is going to be lower than that curve, right? And on the bottom right, it's measurements of the probability that a cooker is in use in France, okay? So now note that the maximum value on the ordinate on the y-axis is a factor of 3 lower than the maximum value on the y-axis in France, and that this is bimodal, and that's rather unimodal. So we know that French love their food. And I guess us poor Brits are closer to the Americans than we are to you guys, but never mind. We all have our crosses to bear. So it's important to take into consideration cultural differences. So here are some examples with a simpler model in which now we only model activities as a Bernoulli process. And again, you can see that we've got relatively good correspondence between the two. Obviously, we've performed quantitative validation, but this is just qualitatively. You can see that there's a pretty good correspondence. So that's for Germany. We can do the same for France. We can do the same for Spain. So I was describing to somebody earlier during lunch that, that there's a wonderful source of data describing people's activities called the Multinational Time Use Survey database. So all of you guys, should you feel the inclination, can do this kind of work, get the data from the Centre for Time Use Research at the University of Oxford. There's a table down here, most of which you can completely ignore, but there's one column called AC, which represents accuracy, and that's really the proportion of truly predicted outcomes. So you can see that, that these are relatively reliable predictive models. We can also predict secondary activities. So that's the probability with which, for example, we'll perform the activity or using audio-visual equipment conditional on the primary activity being cooking, for example, as we tend to see in this lower graph. And we can do that for a whole range of secondary activities, since those secondary activities also have energy consequences, right? Pretty much ignore that table, but that's just to remind me to tell you that we've also developed a model to predict the probability with which a broad range of electrical appliances will be owned by a household, dependent upon the number of members of that household and their socio-demographic characteristics. And again, these are relatively reliable models. Again, those figures for accuracy are fairly convincing. So we can predict the probability with which certain activities will take place. We can assign appliances to households. Well, oh dear. Then we want to predict the use of electrical appliances conditional on the activity being performed. Unfortunately, you can't see that equation, so you're just going to have to take my word for it. That equation is the logit of the probability with which an electrical appliance is likely to be used, which is conditional on the activity taking place. So we have an intercept and a slope, which is a slope of an explanatory variable, which is in itself the logit of the activity taking place, in this case, cooking, because we're looking at the use of cookers. So we can predict the probability with which cookers are likely to be switched on, given that the activity cooking takes place. We can fit a Weibull distribution to predict the duration for which the cooker survives in its on state. Then we use cluster analysis to help us model transitions in what I call fractional power demand. So that's the actual power demand divided by the maximum possible power demand. Okay, so it's got a scale from 0 to 1. So we identified that there are simply 3 clusters of groups of fractional powers that we need to model, and we model transitions from one grouping of fractional powers to another at each simulation time step to predict the dynamics of power demand from cookers. So does that approach work? Well, here we've got some box plots where we compare simulated with observed energy use on an annual basis for different types of appliance. So the box plots on the left are for cookers, then microwaves, then TVs, and then washing machines. And you can see that the median, which is indicated in red, is pretty close between observation and simulation. So it would seem that our modeling strategy is fairly reliable. Here are some, I suppose this is a somewhat dated graph now. It goes back about 4 or 5 years. But this is where, with one of my former PhD students, Fred, we were predicting the use of windows. And in gray, this is the observed number of windows that were found to be open in the laboratory that I used to work in at EPFL. And in black, it's what we simulated. And again, you can see that there's pretty good correspondence between what we observe and what we predict. But I did mention earlier that us humans are a bit weird, a bit, we really are. So here we've got, again, use of windows, right? We've got the probability that a window is observed to be open, and we've got different explanatory variables, indoor or outdoor temperature. So at the top, you've got a couple of graphs that represent a relatively conventional case. So we follow a kind of sigmoidal relationship, right? It's kind of an S-shaped curve, okay? Where with increased temperature, there's an increased probability that a window is going to be open. The next graphs lower down correspond to one of my former colleagues. I won't mention his name, but if you knew him, you'd agree that he is weird. Anyway, so when the temperatures get particularly warm in summer, and this guy predicts or suspects that it's now warmer outside than it is inside, then he closes his window. He actually evolved over a period of time some really clever behaviours. So this is actually a really smart thing to do, and this is a not so smart thing to do. And this is just somebody who's entrenched in habits that he's not going to change for anybody. So he's going to do the same thing no matter what, pretty much. Okay, so we do need to take into consideration individuality, and that's rather tricky. So we've developed some models which we've fit to observations of individuals' behaviours. What we'd really like to do is to fit models in which our regression parameters are defined as joint probability distributions, but that requires very, very large data sets, which we don't have available to us right now. So at the moment, we're stuck with rather rudimentary representations of diversity of behaviours amongst individuals. Here are examples as well of where we can model the position of blinds. In the Lesor, where I used to work, we had strange windows where there was an upper window which opened onto an anidolic reflector, and then there was a lower vision window. So we had to model blinds that were obscuring or not those two different windows explicitly. And so here we could see that we're able to fit models that predict the use of blinds for those two types of windows, again, fairly reliably. We haven't done much work ourselves with respect to lighting, so we've used some other people's work. Way back in '79, a guy called Hunt developed a pretty good model for predicting the probability with which lights are going to be switched on when people arrive in a room as a function of the minimum indoor illuminance. A colleague of mine now at MIT, Christoph, developed a model that predicts light switching probability whilst an occupant is present within their office. And the unfortunately named pig helps us predict the probability with which lights will be switched off at departure. But that's not the whole story. I mean, we also want to predict people's comfort, right? So here's an indication of differences in comfort preferences. So on the X, we've got individuals, okay, and on the Y, we've got the temperature at which they feel neither warm nor cold. Okay, it's their comfort temperature. So you can see that there's considerable variation between individuals, and any kind of predictive model should really take that into consideration. But the exciting thing, for me at least, I'm weird too, is that we can take into consideration comfort feedbacks from behavioral actions. So here on the X, we've got different types of adaptive, opportunity that have been exercised. So a person's opened a window, W. They've made a small clothing adjustment, small c, or a big clothing adjustment, big C. Or they've changed windows and clothing, or have used a fan, F. And what's interesting about this is that systematically, compared with no action taking place, the median comfort temperature is always higher when we do undertake some kind of adaptive action. That means that we derive some thermal benefit from or perceived thermal benefit from the adaptive action having taken place. Now that might be a real thermal benefit. We've opened a window, the relative air velocity close to our skin has increased, which improves convective heat transport from our body. Or it might be rather more subtle than that. It might be more psychological. The point is that we can take these factors now into consideration if we've got good quality field survey data. We can predict now thermal sensation probability distributions. We can go a step further and predict thermal comfort probability distributions. We can even do that taking into consideration the adaptive opportunities that have been exercised. So we can predict the probability with which people are going to interact with their clothing levels, open windows, turn on lights, use a desk fan, and take into consideration the thermal feedbacks to give us a revised prediction of thermal sensation probability distribution or thermal comfort probability distribution. This I'll skip over, I think, but we can also do that to predict the probability with which we overheat in an office. This is a model that seems to have been lost in the annals of time, but it's the only reliable model, or only empirically derived model for predicting overheating, and it can be adapted to model to account for interactions with personal and envelope characteristics. Okay, so that's a kind of a very egocentric tour of behavioral modeling. Does it matter? And this really relates to Eric's presentation earlier. So we incorporated just a couple of those models into an urban energy simulation program that my team developed called CitySim. It's a really, really simple shoebox, okay? It's just an office. And we're only accounting for two stochastic processes, the use of windows and the use of blinds. Okay, and what we see here, well, had I divided by the number of replicates, which was 50, we'd have a probability density function of heating energy use and cooling energy use here. The interesting thing is that you can see that there's pretty much a factor of 2 variation in heating energy use and cooling energy use just from using windows and blinds, okay? Every model, every one of those 50 models is identical. The only thing that's different is the way in which we've randomly seeded the random number generator. So at the beginning of every simulation, we have a different random number at the beginning, which means that we end up with a unique solution for every one of our 50 replicates. And oops, that's what describes that PDF. So now we're trying to generalize things. A colleague of mine, rather modest guy called Jake in the audience over there, is going to be working with me tomorrow to present a multi-agent stochastic simulation platform that he's been developing in the context of his PhD thesis, and is coupled with a single building simulation program called Energy Plus. But that could also be integrated with ConfPlied, with Transis, with ESPR, whatever other dynamic simulation program we're interested in. So his framework predicts, first of all, whether a person is likely to be present using either the model of Jessen that I showed earlier, or using the activity model. So one of the activities is not present, actually, during the... and so the opposite of not present is clearly present, so we can predict when somebody is present at a home, and then we can predict their activities. From the activities, we can make inferences as to where in a home people are. So there's a very high probability that whilst we're sleeping, we're in bed, right? That whilst we're bathing, we're in a bathroom, that whilst we're cooking, we're in a kitchen, and so on and so forth. Now, during a simulation process, we can predict, given the environmental conditions that we predict with our simulation program, the probability with which we use windows or lights or shading devices. Okay, and again, we can produce these similar PDFs of heating or cooling energy use or lighting energy use, as you see on the lower left. But what we need to do is to supplement this this multi-agent stochastic simulation framework with some other models. So at the moment, unlike Eric, we haven't included water usage yet, and we haven't found a reliable basis. Well, we've just acquired data to enable us to develop a meaningful model of predicting use of heating systems or adjusting heating set points. We are doing some work on demand-side management strategies, which we can integrate into this agent-based framework. And the other thing that we want to account for are interactions amongst members of a household, so that we're actually resolving for deliberated processes that lead to some consensual response. And now we also need to, and we'll do this very soon, integrate our electrical appliance ownership and use models. Okay, so that was the egocentric tour. Now a few words about the International Energy Agency Annex, which was the reason I was invited to talk in the first place, and I've got probably -1 minute to do it in. So a year ago, we had a meeting in Paris just before this annex was launched. Sorry, just before the preparation phase of this annex was launched, and I was asked to give some thought as to what kinds of things we ought to try to do in that annex. And that meant that I had to really think about where the pitfalls are at the moment, where the strengths are and where the weaknesses are, and what a good model ought to look like. So for me, a good model fits somewhere within that framework, so presence, activities, behaviours, and comfort. It uses one of the kinds of families of model that I showed you earlier. It's parsimonious, and crucially, it uses parameters that are readily available to modelers. And you'd be astonished in the literature the number of models that use parameters that nobody can predict, that nobody has available to them, and they're completely useless. They're academically interesting, of course, but completely unusable. It should be based on high-quality data, rigorously validated. We use a process that we call k-fold cross-validation to determine the predictive reliability of our models. That's actually quite seldom done. Hopefully, the model is made openly available, and the platform that Jake's working on right now will be distributed under open source license agreement next year. The other thing is that we should honestly declare what the models are good for, and perhaps most crucially, what they're not good for. And we're not very honest at doing that as academics. Or maybe it's not just honesty, we just forget. And when we're using models, we should really be using the state of the art. That's often not done. So challenges, we need consistency in experimental design, consistency in modeling and validation methods, models that are calibrated to good quality data, applications that use the right models for the task, and we need to make sure that our efforts are coordinated. We have many challenges in behavioral modeling left. We need to make sure that efforts are well directed. So the annex is structured like this. We've got 5 subtasks. So from left to right, we've got occupant, presence, and movement. We've got residential behaviours, commercial, and our chair is getting nervous, so I'll be quick. Basically, model development is informing model integration, which is in itself informing applications in design and management to figure out whether these models are really useful. We're doing some work on experimental design, on modeling and validation methods as well. And I'm looking after the subtask on residential behaviors and modeling methods. I think I'll skip this, but there is, well, I'll mostly skip it. We're putting together a proposal to develop an international competition that enables modelers to compete with one another. So given some data set, are you willing to kind of put your neck on the line and compare your predictive accuracy with somebody else's model? Okay, so to conclude, we've made some good progress to predict presence and behavioral actions and appliance ownership and use. We've got a lot of other work to do to model long-term absences. I don't have the time to go into that. Data availability for generating synthetic populations. Eric gave an example of how we can use census data, but that doesn't help us with respect to modeling diversity of behaviors. So that also needs to be resolved. We haven't had a perfect experiment yet. So pretty much all of the models that we have been developed from imperfect experiments that were designed for other purposes. We need generalized transport modeling. We need to account for sequencing in actions. Is the probability of opening a window conditional on the fact that the blind has already been lowered the same as the probability of opening a window given that it hasn't? Okay, so very last slide. So things that we're going to do in this annex. We're going to integrate and harmonize existing models. We're doing that with this multi-agent simulation platform. We're going to define experimental design protocol, and we're going to share data. So at Nottingham, we're going to have a data repository. People are going to have to buy that data, but you don't pay in cash, you pay with data, okay? So you give me, I'll give you mine if you give me yours. You don't necessarily need to provide an enormous amount of data, but if it's considered to be useful, you can get everybody else's. So this is going to be an organic resource that grows. Consistent modeling and validation methods. We need to account for social interactions. There are lots of debates to be had around this subject area. We were having some of them at lunchtime, and more generalized adaptive comfort modeling. That's it. Thank you very much.